Alright guys, so now that you have all the moments and all the forces represented correctly on the cross section, we can proceed by step 5, which is calculate the normal stress at point A. Remember, the question is to calculate the normal and the shear stresses at points A and B. So sigma at point A, as we know, it is a combination of what's happening due to the force plus what's happening due to the bending. Now, is there any normal force acting on the cross section? Of course there is. There is the weight, which is acting in a compressive fashion because it's represented as an X. So you're going to have a minus for compression, very important, minus W over A. Okay, and then you're going to have the bending. Since you have two bendings, so it's going to be plus or minus MYX over IY plus or minus MXY over IX. So recall that since point A lies on the y-axis, therefore the effect of My is going to be 0. So directly, if point A lies on an axis, then the moment about that axis is going to be, so it's going to contribute to 0 normal stresses. So point A lies on the y-axis, alright, therefore MYX over IY is equal to 0. Because X is going to be equal to 0, there would be no horizontal distance between the point and the vertical centroidal axis. So before actually putting in numbers, what do you say in here? Is point A under compression or under tension with respect to MX? With respect to MX, notice that MX separates the cross section into compression zone at the top due to the presence of the arrow and tension zone at the bottom, and so point A is under tension with respect to MX, so this is going to be a plus, and therefore you're going to have in here minus W over A plus MXY over IX. Alright, so minus the weight is 3 multiplied by 1000 to change it to newtons over the area calculated earlier, 12,566, plus the moment about the X is 112.5 kilonewton meter. I have to change it into Newton millimeter. So 112.5 multiplied by 10 to the power 6 multiplied by Y, which is the vertical distance between the point of interest and the horizontal centroidal axis, which is going to be a distance from the center to point A, right? The vertical distance from the center to point A, and it's going to be the outer radius, which is going to be 110. Okay, so it's going to be 110 over Ix, which is calculated earlier to be 63,460,172. Alright, and if you calculate this value in here, you're gonna have minus 3,012,566 plus. Have to be fast in your calculations and very accurate. You have to look at the screen of the calculator while you are inserting in the numbers, because many times you will miss some numbers. So in here you're going to have a 194.77 megapascal. And since the answer is a plus, this means that point A is under tension. Okay, see, usually this is what you're going to get in problems, not 1 million and 3 million like we got earlier in the exercise. Alright, these are logical numbers in here. 194.77 megapascal at point A. Okay, so now that we have the normal stress at point A, step 6 is to calculate the shear stress, right? Calculate the shear stress at point A. So the shear stress, as we know, the shear stress at point A is a combined effect of what's happening due to the shear force plus what's happening due to the torsion. And here you're going to have a VQ over IT plus T multiplied by rho over J. Now look at point A and tell me if there is any shear stress due to the force. Since the shear force is vertical, then when you are calculating QA, you're going to have A prime, Y prime. And A prime is going to be the area above or below the point of interest. And in this case, the point of interest is A. And there is no area below point A. This means that A prime is 0. So in here, A prime is the area, which is the area below point A, is equal to 0. This means that Q is equal to 0 and tau due to the force is equal to 0. So this whole thing is equal to 0. This means that the only thing that's affecting the shear stress at point A is the torsion. And the torsion is equal to 28.5 kilonewton meter. So it's going to be 28.5 multiplied by 10 to the power 6 times rho, which is the radial distance between the center and point, which is going to be 110, over J, which is calculated earlier. So I'm going to just write 2 times 63,461,72, which is 2 times I, 24.7 megapascal. And what's the direction of the shear stress at point A? It follows the torsion and it's perpendicular to the radius. So it is to the right. Okay, because the torsion acts in an anti-clockwise fashion. The shear stress at A is going to be horizontal and to the right, so like this. Okay, because it follows the anti-clockwise fashion and it's perpendicular to the radius. Alright? So now we repeat the process. Now it's very important, there is something new in this exercise. Okay, so step 7, calculate the normal stress at point B. In step 8, you're going to have something new. So sigma at B again is sigma force plus sigma bending, which is going to be sigma force. Since the weight is compressive, it's going to cause compression everywhere, and the magnitude of this compressive stress is going to be uniform, and it's equal to minus W over A, plus or minus mxy over ix, plus or minus myx over iy. Now in here, since point B lies on the x-axis, as you can see, it lies on the x-axis, then the effect of mx is going to be 0. Why? Because B lies on x-axis. Now, what do you say the sign of this is? Is it a plus or a minus? Is point B under tension or compression with respect to my? It's under compression because it belongs to the compression zone of my. So how did I know that? This is my, it's causing compression to the right and tension to the left due to this arrow in here. Okay, so point B is under compression, and therefore this thing in here is going to be a minus. So it's going to be minus W over A minus myx over iy. W is 3 times 1000 over 12, 566 minus my in here is going to be 5.7 kilonewton meter. Change it to Newton millimeter, so 5.7 times 10 to the power 3 multiplied by x, which is the horizontal distance between point B and the vertical neutral axis. So it's going to be 110. Alright, it's going to be 110 over iy, which is 63,460,172. And you're going to get an answer which is obviously going to be under compression, alright, because it's going to be a negative. So in here you have a 10 to the power 6, please change it. Because from kilonewton meter to Newton millimeter, you multiply by 10 to the power 6. So it's going to be a minus 10.19 megapascal. And therefore point B is under compression. Okay. Now, step number 8, which is the final step, very important step, which is calculate what? Calculate the shear stress at point B. And we have that the shear stress at point B is due to the force plus due to the torsion. And the force is VQ over IT plus T. So let's start by the force alone. It's so tau due to the force. It is VQ over IT. Now, is it equal to 0 in the case of B? B lies in here. Is it going to be equal to 0? It's not going to be equal to 0 because A prime, which is the area above or below the point of interest, is going to be so it's going to be either this or the one below it. So it's not going to be 0. Therefore, there is a shear stress developed at point B to do the force. Alright? Now, we have that V, which is the shear force acting vertically, is equal to 15 kilonewtons. So V in here is 15,000 newtons. We have that I is going to be equal to 63,460,172. Now, what is T? What is T at B? What is T at B? Recall that if the shear is vertical, what is T at B? Recall that if the shear is vertical, T is the horizontal length of the solid thickness of a horizontal line passing through point B. Meaning, if we pass a horizontal line through point B, what is T going to be? T is going to be this distance in here plus this distance, because it's the thickness of the solid part. Alright? So it's going to be 220 minus 180. T is going to be 220 minus 180. You'll get these two distances in here, which is T. Okay, so 220, the total, the outer diameter minus the inner diameter, you'll get these two, which are going to be equal to T. So T is going to be 220 minus 180, which is going to be equal to 40 millimeters. So this is in millimeter to the power 4, and this is in newtons. Now there still remains to calculate Q, which is going to be A prime multiplied by Y prime. Now what's A prime? A prime is the area above, let's take it to be above point B. So it's going to be this area. Area of the solid part, right? It's going to be this area, where this distance is 180 and this distance is 220. So how do you calculate this area? So we can write it as the bigger semicircle, which is 220, minus the smaller semicircle, which is 180. Okay, so area prime is going to be, now what's the area of the so this has a radius of 110 and this has a radius of 90. What is the area of the first? So I'm going to call this 1 and this 2. What's the area of 1? It's going to be A1 minus A2. A1 is going to be the area of a semicircle, which is pi r squared over 2. So it's going to be pi over 2 multiplied by 110 squared minus pi over 2 multiplied by 90 squared. So this is, it's going to be 6283 millimeter squared. Alright, and what's Y prime? Y prime is the vertical distance between the centroid of area prime and the neutral axis. So in this case, we're talking about the horizontal. This is the horizontal neutral axis, or the horizontal centroidal axis. I'm not going to call it neutral axis because it's not neutral. Recall, when we have double bending and the force, the neutral axis is not neutral. And to find it, we need to set sigma equals to 0 and get the equation of a line. So Y prime is the vertical distance between the centroid of A prime. So it's the vertical distance between centroid of A prime and the horizontal centroidal axis. Now here's the question. Where is the centroid of this section located? If you told me 4r over 3 pi, you're wrong. Please, very important. Now, we know that for a full semicircle, when there is solid everywhere, I agree with you that the centroid is located 4r over 3 pi from the diameter. But this is not the case. Our case is not a complete, our case is this. How do I find the centroid of this thing? This is a composite cross section. This is the same thing as you're dealing with a T-beam or an I-beam. Okay? This is a composite cross section. And to be able to deal with that, what you're going to do is you're going to divide it into something that you know. And what you know is the semicircle. So what you're gonna to deal with it, you're gonna divide it into the outer semicircle, outer whole semicircle. So this is one with diameter of 220 minus the inner, which is gonna be 180. Okay, this is it. So to determine, so very important remark. Okay, so A1 is the area of 1, which is the half the area of a complete circle. So it's going to be pi over 2 multiplied by 110 squared. So pi over 2 multiplied by 110 squared. Area 2 is going to be pi over 2 multiplied by 90 squared. And area total, we have already found it to be 6283. So this is 6283, which is going to be area 1 minus area 2, depending on how we segment it. Okay, depending on how we segment. So 6283. Now this is going to be, so pi over 2 times 110 squared. This is 19006, and the one below is going to be 12723. Alright. Y1 bar, of course we need a reference to calculate Y1 bar. Let's choose this reference from the bottom. So Y1 bar, now you can say that Y1 bar is going to be equal to 4r over 3 pi, because the section is complete, it's solid, there is no hollow space. So 4r over 3 pi is the distance from the diameter to the centroid of a semicircle that is complete and it's solid. So now in here it's going to be 4 multiplied by r1, which is 110 over 3 pi, and in here you have 4 multiplied by 90 over 3 pi. Okay, and then you can calculate y bar. So let's calculate these things in here. So 4 times 110 over 3 pi, 46.685. So this is going to be 38.197. So it's going to be 38.197 millimeters. And now you can find the centroid, right, from the reference that is shown in here. Alright, and to find the centroid, remember, you have to always account for how we divide the section. So in here it's a minus. Okay, we subtracted two semicircles from each other, and therefore in here it's going to be A1, which is 19006 multiplied by Y1 bar, which is at the same time what? It's at the same time y prime, because the reference is taken to be at the neutral axis. Okay, so this is going to be equal to y prime. Whenever the reference is taken to be at the neutral axis, you're going to get y prime equals to y bar. So put this as a remark. Okay, whenever the reference is taken at the neutral axis, y prime is going to be equal to y bar in this section and in the chapter, in that of chapter 7. All right. So y prime is in here is going to be the y prime by definition is the vertical distance between the centroid of area prime and the neutral axis, which is what we got in here, 63.87, and therefore q is going to be equal to a prime y prime, where a prime is 6283 multiplied by 63.87, and 63.87 times 6283, you're going to have a 401. You're going to have a 401.295. All right, millimeter cubed. So this is your cube. This is your cube. All right. Now, what is t? What is t? The thickness t at the point of interest. All right. What is t? So we're trying to calculate the shear stress at point B. All right. So if we go to the cross section, look at point B in here. So draw a horizontal line because the shear is vertical. All right, we are calculating the shear stress due to a vertical shear force. Draw a horizontal line and see where it cuts the solid cross section. So it's going to be these two, all right, these two things in here. So you have this and this. How do you find these distances? You're going to subtract the 220 from the 280, from the 180. 220 minus 180, you get these two distances which represent t. Alright, so t in here is going to be equal to 220 minus 180, which is going to be equal to 40. Alright, so here you have 220 minus 180, which is 40 millimeters, and then you can find tau due to the force equals VQ over IT. Alright, V is what? V is the vertical shear force, which is 15,000 newtons. So let me write it in here. So 15,000 newtons and this is going to be a 2.37 megapascal. It's not sufficient to calculate the shear stress alone. We have to find its direction, and due to the force, we look at the direction of the force. The direction of the force is vertically upwards, so the direction of the shear stress due to the force is also going to be vertically upwards. Remember, the direction of the shear stress due to the force always follows the direction of the force. If the force is upwards, then the shear stress due to the force is going to be also upwards. Now, remember, we still have the effect of the torsion, which we didn't account for yet. So if we go in here and we put the shear stress due to the torsion, the formula is T multiplied by rho over J. Okay, it's going to be T rho over J, where T is the torsion. Alright, and we have the torsion. Okay, so we have the torsion to be 28.5. So 28.5 is the torsion, 28.5 kilonewton meter. So 28.5 kilonewton meter multiplied by 10 to the power 6 to change it to newton millimeter, multiplied by rho, which is the radial distance between the point of interest and the center. And if you go back to the figure, this is the cross section, right? And you have point B to be on the outer radius, and therefore on the outer circle, and therefore the radius in here is going to be what? Is going to be 220 over 2, which is 110. Okay, this is going to be your rho, so it's going to be 110 over J, which is 126,920,340. Okay, and in that way you can calculate the shear stress that occurs at point B due to the torsion, because remember, the shear stress at a point is what's happening due to the force plus what's happening due to the torsion, plus or minus. We're going to see depending on the direction of the torsion. So this is going to be 24.7 megapascal. We still need the direction. And what's the direction? How do we find the direction of the force due to torsion? It follows the direction of the torsion, the direction of the shear stress due to the torsion. It follows the direction of the torsion, and it's perpendicular to the radius. Okay, so the direction of shear stress due to torsion is perpendicular to the radius, and it also follows the direction of the torsion. So direction of shear stress due to torsion is first perpendicular to the radius, plus it follows the direction of the torsion. So if we go back to the cross section, we have the torsion acting clockwise or anti-clockwise. Let's see. So if you go back to the cross section, we have the torsion acting in an anti-clockwise direction. Alright, and so the torsion at B is going to be vertically upwards, because it's gonna follow the anti-clockwise direction, and it's gonna be perpendicular to the radius. Okay, so it's gonna be vertically upwards. So notice in here that the direction of the torsion is gonna be the same as the direction of the shear stress due to the force. Okay, so this is gonna be upwards. And now we can find tau net, which is going to be what? It's going to be 24.7 plus what we got earlier due to the shear, which is 2.7, I think. 2.37 plus 2.37. 37. Why did I add them? It's not always the case where I add the shear stress due to the torsion and the shear stress due to the force, but I add them in this case because they have the same direction. Both are directed upwards. They have the same direction. So you're gonna have a 24.7 plus 2.37, and you're gonna end up with 27.07 megapascal directed upwards. Alright, directed upwards. Perfect. This is it. So to find the shear stress at a certain point, break down into shear force and torsion. Shear force, in this case you have a vertical shear force, so it's going to be, the area prime is going to be the area above or below. And the main takeaway of this exercise is that whenever you have a hollow cross section, we need to apply the formula for the centroid to be able to locate y prime and hence calculate q. Okay, so whenever you have a hollow circular cross section, this is what you do to find q and y prime, and then you can easily find tau due to the force and tau due to the torsion. If they have the same direction, you can add them and find the net shear stress at the point of interest with this direction. If you have any questions, let me know please, and I'll see you in the next video with another exercise concerning Chapter 8.